Hey everyone, welcome back to the PID Fundamentals tutorial series with SimTune. In episode 2, we are talking about the PID equation. And we're going to touch on this briefly. There's a lot to go over with the PID equation, and we're not going to try and handle it all. So I'll post some links in the description below that are really good resources if you do want to dive in deeper. But we mostly want to touch on the PID equation to set up for the next few episodes where we'll be talking about the proportional term, the integral term, and the derivative terms independently and what each of those do. So first let's talk about the controller feedback loop. Then we'll point out what the proportional, integral, and derivative terms are. And then we'll talk about the different forms that you might come across of the PID equation. So let's first go to SimTune and pull up one of the simulations. This is our simple flow simulation, which is depicted here. And let's just demonstrate what a PID controller does. So right now we're not incorporating the PID control because we're in manual, so we're giving the command to the control valve ourselves. So let's begin. We'll keep it at 0, and you'll quickly see that nothing happens. And that's because we're just telling the control valve to stay closed. And we can manually control this, and we can bring it up to set point. In fact, since this is kind of linear, I know that if we go to 50% of our control valve, it will bring our process up to our set point, which is about 50% of our range. Okay, so that is running it in manual. If we incorporate the PID controller, we actually get the same performance, but done automatically. And this is actually an example of bad tuning, but as you can see, the PID controller is trying to get the process flow to reach the set point that we're giving it, 350. Okay, so that is an example of the feedback loop in action. So let's look at what that feedback loop is. If we go to the PID tuning guide and scroll down really quick, this is a diagram of our feedback loop. So we gave it a set point, and the sensor or the measurement device gave us a reading of what the flow was, and an error was calculated. So the difference between the set point and our process variable. Then the controller, the PID algorithm, takes that error as an input and spits out a command. And the command, in the case of our simulation, went to the control valve. So the control valve was adjusted by the PID controller, and the process then responded to those changes. Then the measurement device gave us another reading of the flow, and the interval was looped again. And the controller just keeps trying to make changes to get the flow up to the set point. So now that we've gone over the feedback loop, let's talk about the PID equation. This is the portion right here, the controller portion. Really, like I said, it takes the error as an input and it calculates an output. And here are the different sections of the PID equation. We've got our proportional term, our integral term, and our derivative term. And each one of these has a different tuning parameter, and that's what we adjust when we tune PID controllers. And each one of these utilize the error in a different way. And in the next few episodes, we'll talk about each one of these terms and how they utilize that error, and how by making adjustments to these different tuning parameters, you can really make a different performing PID controller for different scenarios. Now let's talk about the forms of the PID equation. This one right here is a generic form, and it's actually called the positional form because it's calculating an output. Whereas if we come over here, we can see a different form, and this one is called the velocity form. It calculates a change in the output. And as you can see, it looks different. We still have the same components. We've got our proportional term here, we've got our integral term here, and our derivative term here, but each one of those looks different from their corresponding parts here. Our proportional, our integral, and our derivative. The velocity form is actually derived from the positional by just taking the positional at the nth interval, or the current interval, and the previous interval, n-1, and you subtract the two and turn it into a change in output. And it really is just simple math to make that subtraction, and you'll come up with an equation similar to this. And on top of that, really to be clear, on top of positional versus velocity, we also have different variations of the PID equation itself. So for example, we've got the Allen-Bradley. We can see that it changed a bit, but not too much. But if we look at the Allen-Bradley independent gain form, you can see it's considerably different from where we started. In addition, Honeywell and other companies came out with their own variations of the PID controller, and each one, it's just really important to make sure when you start tuning a PID controller, you know what the form of the PID equation is, and you educate yourself on what that form of the equation incorporates. For example, this one, the tuning parameter is in the numerator rather than the denominator. So you need to know that before you start tuning. Those are different things to keep in mind about the PID equation. And like I said, I'll post some links in the description below if you want to learn more about the PID equation. But really, we'd like to move on and talk about each term independently, starting with the proportional term. So thanks for watching. Hopefully you tune in for the next one, and we'll keep going more in depth about PID fundamentals. Thanks.